The next presentation is entitled Influence of the Impact Speed on the Damage of a 7075-36 Hourglass Specimen and Finite Element Study. So we are talking again about impact damage. The work is from Arcieri, Baragetti, and Professor Bozic from the University of Zagreb. So first of all, impact damage is a big concern for many applications, and in particular for aircraft engineering, aerospace engineering. There is a typical expression in this sector that is foreign object damage. It means that there are some particles, debris, sands, they say also rivets, that are on the piste and that can be ingested by the engine during takeoff, landing also birds, so in this case, and landing. So the problem is that we have the appearance of craters, nicks, dents, and other defects that can propagate and reduce the fatigue strength, causing also some disasters. So which are the mechanisms involved? We have the appearance of microcracks, of microstructural damages, and the appearance of stress concentrations that, as known, decrease the fatigue strength of components. But we have also the introduction of residual stresses that can improve or decrease the fatigue strength of the components, according if they are tensile or compressive. In case of compression, we have an improvement. In case of tensile stresses, we have a decrease. It is the same mechanism of shot pinning, more or less. In shot pinning, you have a global effect, so all the surface of the component is under compression, or the area a little bit below the surface. In the case of foreign object damage or impact damage, you have a localized effect. So you have tensile stresses that are dangerous. In literature, the studies focus on plane and airfoil geometries, as just seen. And now we want to study other geometries, which are, for example, it's some years that we are studying the case of the impact of a sphere against an hourglass specimen made of 7075 aluminum alloy that is used in aircraft engineering. We are using hourglass specimen because the objective is then to test this specimen under rotating bending loading and to assess the fatigue strength. So in a previous conference in Dubrovnik, we presented a work that was on the study with a design of experiment technique, the Taguchi method, applied on the finite element results of some simulation. And in particular, we studied macroscopically the effects of the parameters, of the impact parameters on the stresses after impact in the axial direction. In the axial direction because we want to test this specimen with rotating bending stresses or axial stresses, cyclic axial stresses. We studied the effect of the impact speed. We tested two levels of impact speed, of the material of the ball, steel and ceramic, the diameter of the ball, two impact angles, alpha and beta, that are measured on two planes that are perpendicular to each other, and the parameters E1 and E2 are the empty factors. So factors that formally have two levels, 1 and 2, but in practice, they are 0. And they are used because after processing according to this methodology, you can see that if you have forgotten some significant parameter, if the result of your calculation is that, for example, E1 is the significant parameter, so in your study you have forgotten something. And the result of this calculation, you can see that we carried out only 8 finite element analyses in order to test 1, 2, 3, 4, 5 plus 2 parameters with 2 levels. So we reduced a lot the computational time, we have only 8 runs. According to this result, according to this study, we found that the velocity, the impact velocity, is the most significant parameter on the stress state in our specimen. And so for this reason, the objective of the presentation of today is to discuss how the impact speed influences the damage in a 70-75 T6 hourglass specimen to find the trends. And due to the fact that we have found that the impact angles are not so significant as the impact speed, we are considering only normal impact. Here we have the finite element model created for the impact simulation. We have the hourglass specimen that is made in aluminum alloy with the mechanical properties reported. We used an elastic, perfectly plastic behavior. And then we have this sphere that is modeled as a rigid component. And so the material, the inertial properties are set to the center of the sphere. The boundary conditions are based on the test rig that we have in our lab. So the cylindrical parts are fixed in the holder, in the specimen holder, and with 2 set screws. And we have placed the sphere very close to the hourglass specimen because we are neglecting the effect of area and gravity. Air and gravity. Sorry. Okay, so we validated this finite element model for one impact case, an impact velocity of 100 meters per second. And here you can see what happens after the impact if we load the specimen with a rotating bending moment. So you can see different bending moment positions. And first of all, you can see that the critical area, comparing with the results of the fracture surface of the tested specimen, is that that we have crack appearance in the areas where the maximum axial stresses occur during a loading cycle. We simulated only one cycle using a static calculation. And then we have also cracks propagating from the surface of the dent created by the impact, but we haven't simulated micro damages, and we have only an elastic, perfectly plastic material behavior, so we don't simulate it. What it happens is, what we can observe is this area where there is a step discontinuity. This area, according to our finite element results, is subjected to compression during the wall loading cycle. So the appearance of the discontinuity can be due to the resistance provided by this area of compression. There is a time in which this area is surrounded by tensile stresses, and so the discontinuity appears. This model, the finite element model, I repeat, was validated only for one impact speed. So let's get let's go to the objective of this presentation. What study was the influence of the impact speed on the dent depth, and as we can see, the trend can be parabolic or cubic. The R square is values are very, very close to 1. But if we neglect the small impact speed, you can see that the parabolic trend is good. We have only a very, very small variation in R square. What is strange is what happens to the axial stresses. Because the trend, here we can see the trend for axial stresses in the wall specimen and in the minimum cross section where the highest total stresses are expected to occur during the fatigue loading. So you can see that we have an increasing trend for small, very small velocity, then a decreasing trend, then again it increases and decreases. It's a strange trend, and maybe there are a lot of motivations to explain. First of all, the material law used, that is elastic, perfectly plastic. So we have a saturation of the stresses that the specimen can support. So when we have the elastic recovery, we have this trend. The second reason can be that it is not the case of the impact of a sphere on a plane, for example, but when the impact speed increases, the area that resists to the penetration is higher in this area, for example. Here, this resistance, this area is a little bit higher than the area in the minimum cross section. And then we have a cooperation of a larger part of the specimen due to the higher penetration. So these are at the moment the possible reason. Then we have no the simulation of micro damages. It's possible that at high speed we have micro damages, and also some portions of the material are detached from the hourglass specimen. So, in conclusion, I have just presented the finite element study to analysis to study the influence of impact speed on damage in a 7075 with a 6 hourglass specimen. The only conclusion on which we are more or less certain is that the depth is a parabolic trend, while for the axial stresses we have a strange trend. Now we are working on the implementation of other material models. We are working on Johnson-Cook model also with damage if we achieve our goal. And then we are carrying out also experimental tests at different impact speed. And we want to study then the fatigue strength of the impacted specimen. And we want to study the influence of other impact parameters. The final goal, but I think that we will reach in many, many years, is to have a model that can predict from the beginning to the final step what happens. So from the impact damage, the notch depth, the dent depth, then the stresses in our specimen and the fatigue strength. So we are working again on multi-axial fatigue due to the presence of the dent. Thank you for your attention.